Okay, so I'm Ayaz and I'm back with. Is this voice okay? It seems to be echoing. Okay, cool. So what we're going to talk about in this session is how do the instructions get executed on CPUs, and then we'll discuss how do you add your own instructions. And before actually we really start doing anything or I start discussing things, I want you all to basically build the gem5 binary for RISC-V so that it'll just save us some time when we add our own changes in the simulator and rebuild the binary. So just run this command in your code spaces and let it build the binary in the background. Okay, so hopefully most of you have already executed this command. So before I actually dive into the outline of what I'm going to talk about, or the more specific things we're going to talk about, I just quickly want to reiterate what Jason said, that the goal of this session is to make sure you feel a little bit, or at least somewhat confident about adding your own instructions in gem5. Apart from that, I guess the other goal is to make sure once you look into that code base, you know what's going on there, right? So that. Oh, so this is the in developing gem5. The developing gem5 component, you'll see CPU instructions PowerPoint. Yeah, and so thanks for reminding me that. I think it's a good idea to have your PowerPoint slides open. So if you can't see anything from here, at least you know what I'm talking about.
Sorry. That reminds me, let me interrupt for a second. On the bootcamp info website is a lot more detail than especially in this part, there's lots and lots of pages of text that I wrote years ago for learning Gem 5 that we kind of copied in. So we're kind of jumping through a lot of it in each session. So yeah, I'll talk more about that.
Okay, so that brings me to the outline of what we're going to discuss today. So we'll start with the basics of what an instruction set architecture is, how the instruction set architectures and the CPUs that are implemented in gem5 they interact with each other, some of the other high-level concepts that you need to understand before you start understanding how instructions are really implemented. Then we'll look at a couple of instructions and try to basically cache their execution at some points inside gem5, and then try to relate that to some corresponding code and basically see how exactly an instruction flows through gem5 while executing. And then we'll see how exactly the C++ code that is implementing instructions in gem5 is generated. Actually, that is not written by someone. It's auto-generated code. But how is it generated is through a domain-specific language. And we'll see how really to understand the code that you see in that DSL and how the code from that DSL is basically then mapped to the C++ code. And then we'll do a couple of exercises of adding a couple of instructions. And we'll also test those. So, okay, let's start with what is an ISA. Anyone who want to give an answer? What do you think? What's an instruction set architecture? Yeah, yeah.
It's like the vocabulary between the hardware and software.
Cool. What do you think are the components of an instruction set architecture generally? I mean, it does not have to be exhaustive list, but any component you could think of.
Like addressing modes, instruction kinds,
Yeah, yeah, cool. Anything else? Cool. Yeah, memory consistency model. Anything else you can think of? Yeah, that for sure. So I think, yeah, that are a few of the components. A few examples here, just to reiterate what some of you said. Instruction set architecture really is the this interface between the hardware and the software. And as you can see on the right side of the slide, the entire computing stack, the instruction set architecture lies between the software components, purely software components, and the purely hardware components. And instruction set architecture, though, includes a lot of things, starting from the instructions to what are different registers that are supported, memory model, how exceptions are handled, and all of that. What we are going to be covering mainly today is the instructions part of it, which I guess is probably the most important thing, right? Because that's how CPUs do work. So before we go into more details, I think one important concept that we need to understand is the CPU and ISA independence in gem5. As you might know, there are many CPU models in gem5, right? There are also many ISAs that are supported in gem5. So to ensure that the cross product of two is supported, and like you can run any ISA with any CPU model, gem5 tries somewhat to keep the two independent. But obviously, it's a very hard problem to solve, right? Like there is an inherent dependency between the ISA and the actual CPU that is then built using that ISA. So we'll look at in gem5's models, or gem5's a system that gem5 is modeling, what parts are purely ISA dependent, what are totally ISA independent, and then what are somewhere in the middle. But before we do that, we need to understand, I think, another important concept, which is how do the CPU models and the ISA components talk to each other, right? Or what's the API between the two? So primarily, there are two interfaces, or two generic interfaces, static instruction objects that are used by the CPU to access the ISA, or to access the instructions, right? And then the other interface is execution context interface that is used by the instructions to access the CPU. Again, we'll look at more details of these two interfaces. I just want to give you a very quick overview of what are two generic interfaces that are largely used when it comes to the interaction of the CPU model and the ISA system. OK, so this brings me to that big picture of gem5, a system that gem5 is modeling. And if you look here, so the first thing, these red blocks, these show mostly the totally ISA dependent components. So for example, ISA description obviously has to be ISA dependent, right? Like how really you specify the dependent on an ISA, the instructions and all that has to be totally ISA dependent. And how do you decode those instructions will depend on the ISA itself. TLBs usually are obviously ISA dependent because they might do, ISA might specify handling TLB in software, or a part of that in software and some part in hardware, so it has to basically rely, or the model itself has to be ISA dependent. Similarly, we have interrupt controllers and fault handling, all that. Those components in gem5, these models in gem5 are ISA dependent. Other components which are ISA independent, memory system is an example. In gem5, it is mostly ISA independent. So it doesn't matter which ISA you're using, it will behave exactly the same way. Then there is something called a decode cache, which is just, in gem5's terminology, is like a container where once your instructions are decoded, you put them in some kind of a cache or a buffer. The two important things that I want to point out here are the execution context that you can see somewhere in the middle in one of the red blocks, and the thread context, which is on the right side. So again, this execution context itself is ISA independent, but as I was telling you earlier, that this is used by the instructions to access the CPU state. But yeah.
If addressing mode is like part of the ISA, within the cache and the memory systems also be like ISA dependent, because the ISA
So the ISA would specify, in case of gem5, you would have whatever like parts of an instruction correspond to the address, or how do you compute an address, that is totally like kept independent of once a request is sent to the memory system. So that's why the ISA specific parts are handled in a separate system. And then once you compute the address, depending on the address mode, you just send out a request, and which is in a system which is totally independent of the ISA. So this is, from gem5's point of view, this is done to be convenient to make gem5 able to basically be used with different types of ISAs at the same time, right? So execution context, as we just talked about, is the interface or the API between your instructions and CPU. Similarly, there is another interface which is very similar to execution context called thread context, which is also used to access the CPU state, but it is used largely by other components of the system, like system calls or the processes, especially in SC mode. So, but there are a lot of similarities between thread context and execution context. And the other components that we haven't talked about, which have so far we were not in those red boxes, those components are mainly ISA independent as a base, but usually you will inherit that base and make it ISA specific. An example of that will be static instruction. So static instruction, which is shown at the top of this diagram, is basically, as a base class, is ISA independent, but usually every ISA will inherit from that static instruction and will have an ISA specific static instruction. And static instruction, if you remember a couple of slides earlier here, I showed you that this is the interface between the CPU and the instruction. CPUs, the way they access the ISA subsystem is through the static instruction objects. So in summary, static instruction object corresponds to a single static instruction. OK, so coming back to our outline, we have tried to cover a little bit of how this independence of the ISA and CPU is maintained in gem5. We'll now try to cover some more important high-level concepts that, again, will be used once we go into more details of looking at exactly how an instruction is executed and how exactly do you implement an instruction. So the two things that I guess you need to understand the difference between are static instructions or static instruction object or class, and the other one is dynamic instruction or inst. So the static instruction basically, as the name might suggest, has all the static information about an instruction, like what's the operation class, what are the source and destination registers. It usually maps to, there's a one-to-one mapping between the static instruction and the actual, the binary instruction or the machine instruction. Might have flags to show if this static instruction is going to be decoded into runtime smaller micro operations or dynamic operations. And then a static instruction has some virtual functions, which basically define how exactly this instruction will be executed. Examples of the functions are execute, initiate access, complete access. And we'll look at actually in more details of these functions. So don't worry if you don't really get the idea, but just try to keep this in your mind that there are some functions, some virtual functions static instructions have, which we're going to talk about. And it might have disassemble functions, which are basically there just to create a disassembly or disassemble the instruction for you to be readable. The dynamic instruction, in contrast, is basically an example of execution context itself. And what a dynamic instruction usually have, it's mostly used by the more detailed CPU models. The cases where you can imagine that the instructions at runtime might have to go through a lot of phases, right? Like in case of out-of-order CPU models, the instructions might use physical registers, and they might be using the static instruction registers might be mapped to some or renamed to some other physical registers, right? So they're like phases of instruction or the phases of I would say, different phases that instruction has to go through. So basically, dynamic instruction tries to keep track of all of that. And the information it might have is like the program counter, and if there is next program counter that is predicted once you start running that instruction. The result of the instruction, you might need it in some cases. If you have multiple threads, then what's the thread number, CPU it's executed on. If you have renamed the static registers, then what indices are, or what are the rename register indices that you rename the static registers to. So that's basically the this and any other thing you can think of, which is the dynamic information about an instruction, will usually be in the dynamic inst class or dynamic inst, which is itself just a type of execution interface. So going back to execution context that we talked about previously, that it's the interface between the CPU, between the instruction and the CPU. So execution context allows an instruction to access the CPU state, right? So as you can imagine, to access the CPU state, an instruction, what it might want to do, it might want to access the program counter at some point, right? It might want to access some other registers in the CPU, right? Or any other part of the CPU state, right? So all those things, usually the instruction accesses through the execution context interface. Does that make sense? What an instruction might do through an execution context interface? OK. Can anyone answer why the instruction wants to do this? Like why an instruction might want to access the program counter? Mm-hmm. Yeah. For example, if it's a jump and it has to use that to jump somewhere else, right, to compute the effective jump address. So you can think of other ways where instructions might want to access the CPU state. I guess thread context, I talked a little bit about it, that it's another type of context. Again, mostly not used by instructions, but used by other parts of the system to access the CPU state. And they are very similar, the two context interfaces. OK. So I think at this point, we are going to go to look at how exactly an instruction is executed. Like once you just run some instruction, I mean, you run some benchmark. Obviously, it will have some instructions. And if you look at just one instruction inside that benchmark, what are different functions that get called, right? So at this part of our session, we'll cover that by running a GDB-based execution. But then in the next part, we'll look at the code we are looking at right now, how exactly that code is, a part of that code is generated, right? So the idea is that if you don't understand everything, that's OK. We'll look exactly a lot of that code, how that is generated. At the same time, the execution flow we might go through, a large part of that code probably is just not important for you to understand at this point, right? I'll try to emphasize on what is the most important thing you should look at. But we'll try to do this together so that you have you have the same GDB execution running on your computers, and you can look at the things that I am doing here, OK? So for this, what we're going to do, we're going to are your binaries already compiled? OK, cool. OK, so I'll switch to code spaces. Well, technically, at this point, I think what I'm using, the binary that I'm using is, it should already be there. Okay, so you can open up your slides as well to see the couple of next things you have to do. The first thing is that we're going to use the same script we used yesterday to basically run some benchmark again, a very simple simulation that we'll then try to debug through or go through. So what I'm going to do is that I am in gem5, and I'm going to get the script that I used yesterday. Let's see. By yesterday, I mean it should be in materials using gem5, CPU models, and then let's go to the finished material, and let's get the CPU models normal cache one. I am just copying it to my current directory. Here, I'm going to rename it to something else. So it's called CPU models -normal -cache.py. I'm renaming it to instruction trace. And then let's open this script. Okay, so do you all have this script with you now? Okay. Couple of things that we're going to change here. Let's make sure the CPU we are using is timing. We're going to first use a timing simple CPU. Yeah. Just in the current directory where my gem5, inside my gem5 folder. You could do it anywhere, but just to be consistent so that like we're doing the same thing, I have this in my current folder where gem5 is. And the first thing we're going to do is we're going to use timing simple CPU. So we change the CPU types to timing. And the other thing I'm doing is I'm pretty sure actually the binary we already, well, this binary is for x86, so it's not going to work. We need a RISC-V binary, but we can use any binary, and the instructions we're going to look at, any binary should have those simple instructions. But to be sure we are all doing the same thing, I'm going to use one hello world program from the tests in gem5. So that exactly, if I am in gem5 directory, should be tests, test programs, hello. Okay. Okay, so that's the binary we are using, the hello binary in the tests of gem5. And the script we have is what we used yesterday. Do we all have the same script now? And so if you just run it with, if your binary is already built, the gem5 binary, use that binary to run it, or I'm just using the one that already exists in the code spaces, gem5 RISC-V. Use that binary and just use it with this script, and the program should execute, right? You should be able to see the hello world being written on the terminal. Right? To run. So I've just used gem5-RISC-V. So it's RISC-V gem5 binary, which is already in this environment. I'm just passing a Python script, which is creating this simple system, which is exactly the system we used when we were discussing the CPU models yesterday. Can you? No. Have any one of you already able to run this simple thing? Okay, cool. So while some of you are trying to run the workload still, I want to ask a question. What do you think that, what are the two most important parts? Well, there can be many important parts, but what do you think are the two most important parts that are needed if you want to like implement an instruction in a simulator? What might be the two most important parts? And let me like maybe elaborate the question a little bit. So I'm really trying to ask, what do you think in terms of correctly implement an instruction? What are the two most important aspects you might have to think of, given some ISA you are aware of? Yeah, like how to figure out that what instruction this is. Yeah, so that's related to decoding the instruction, right? Like to figure out how exactly the instruction is encoded, and then once you get some, you fetch from instruction cache some bytes, right? A cache line. How do you figure out from those bytes what exact instruction this is, right? And that usually you do by decoding some fixed length of bytes, right? So that's one of the most important things. In order to obviously implement an instruction in a simulator, you need to be able to understand how exactly the decoding is going to work. What might be the second most important thing? Sorry?
The semantics, like
what actually it's going to do?
Yeah, given this instruction, that means memory operation.
Exactly. So that specifies what exactly the operation it's going to perform, right? And dependent on the format of the instruction, it might just access some registers. It might access memory. But whatever is that operation is probably the second most important thing, right? There are many aspects to that, but as a general concept, I guess that probably is the second most important thing. So what we're going to actually do is that we are going to put some breakpoints in while running gem5 with some benchmark, and actually try to, for some specific instruction, try to see for these two important things, like how exactly at what point the instruction gets decoded. In the ISA subsystem, what made it do, how do you trace it all the way back to the CPU, right? So CPU must have talked to the ISA system and said, oh, decode this instruction, or decode these bytes, right? So how does that flow look like? And the second thing we'll look at is when the CPU said, oh, execute this instruction, and what exactly is the behavior of the instruction, it would have asked the ISA subsystem, right? So again, how would that flow look like? So let's now move to, what we'll try to do is we'll jump back a little bit between just running this thing with GDB and then looking a little bit of the source code separately as well. So let me start with by just using GDB. Have you all already, I'm assuming you must have used GDB previously, right? Or most of you? Okay. Or like at least you know what's GDB. Okay. So let's pass our binary, which is gem5 RISC-V. Okay. So my binary is loaded. Are you all able to load the binaries? I want you all to also do the same thing so that you also know exactly what's going on, right? If it's too hard for you to like do and also follow at the same time, you can maybe not do if you want. I'll strongly suggest like you try to do it as well. And what I'm going to do, I'm going to put a couple of breakpoints. So the first breakpoint is, so the instructions, first of all, I forgot to tell about the instructions we're going to look at. The first instruction is a simple add instruction in RISC-V. And to do that, the first function I'm going to put breakpoint at is called add function. And we'll look at this function, but this function, what it really does, or what it is really responsible for, is like when the instruction is actually decoded and its object is created of a static instruction. This is the function where it happens. So I just put a breakpoint there. The second breakpoint is at, also this is in your slides as well. So if you are not able to see exactly here, you can look at your slides and see where exactly are the functions where I'm putting the breakpoints. And the other one is specific to add an execute function. So inside the add class, we have an execute function which defines how exactly this add instruction is executed. So I'm putting a breakpoint there as well. So I've got 2 breakpoints. Are you all able to put these 2 breakpoints? Okay. Okay. Anyone? Should we move forward? Okay. So let's. Okay, sorry. First thing we have to do, we have to run. So in GDB, inside GDB, you use run command, and then you just pass the argument, which you will use with your actual binary that you're trying to debug. In our case, it's just one argument, which is the name of the script we want to use. So that's inst trace, right? That's what we named our script, right? Oh, it's a dash. Oh, I named mine, I think, underscore. Yeah, no, it's dash. You're right. Okay, so yeah, make sure whatever is the name of your script, just use the same name. So in slides, it's probably underscore. What I'm calling it here is dash. So in dash trace, whatever the script is. So just run it. Our program started to run. Wherever the breakpoint was, it stopped, right? And what you can do is you can always, in GDB, you can trace back and see what functions got executed before this function. What is the flow of functions? That's what we want to look at first of all. So I'm going to backtrace randomly for like 10 previous function calls. All of them are not going to be important. We'll only look at the ones that are important. Well, let's say I just backtrace for the last 10 calls. And this is what I've got. Now, you don't really need to look much into anything which is after this 5th function call here, which are relevant to how an event is triggered, or in gem5, it's simulation loop, whatever is going on there. You don't have to worry about it at all. At this point, what is important for us is really to understand, starting from a CPU model, what it did for an instruction to get decoded, right? So even without going into the actual implementation of the function, you can look at, starting from function 5, there was our timing simple CPU model triggered the instruction cache port there, triggered some event, said, OK, I've got some response. If we'll look at exactly these things, we'll figure that out, what exactly there was happening. But you can imagine that from instruction cache, you'll get some response, which is your actual instruction bytes. And then in simple CPU model, we have a function called pre-execute. We'll look at that function, but let me just quickly go through this flow here. So this pre-execute function is basically responsible for anything in timing simple CPU that happens before you execute the instruction. So if you remember from yesterday, we said timing simple CPU is a single cycle CPU or a CPU model which executes one instruction in one cycle only, right? If it's a memory operation, it might take longer. But otherwise, it just executes one instruction in one cycle. So before it executes that instruction, there's a function called pre-execute, which gets called, which is then responsible for actually, from whatever you got the instruction cache bytes you got, it is responsible for then decoding those bytes into your actual instruction. So in this case, from pre-execute, then we've got some ISA-specific decode function calls. Okay? So let's maybe open these functions, some of them, and see and try to understand a little bit of them. So let's start maybe with this pre-execute thing, which is from the base simple CPU, which is what the timing simple CPU inherits from. Yes.
So has it gone through all those, like, I think I might have missed it. So say on add, decode instruction, and decode something. Does it pass those already?
So if you have
Pass those steps already, like those functions, the ones that have been.
So that's the last function that got executed. So we are trying to look from the beginning to the end. So the CPU is going to tell the ISA subsystem, right, that I need to decode this thing, so decode it for me. And the CPU finally creates that add instruction, which is at the top. But we're trying to look at how exactly the flow might look like, right? So if you look at so that's what I was trying to do. In our simple CPU model, so in base simple CPU, this is the pre-execute function that we just looked at in our when we backtraced the execution. Okay? It'll be good if you can open this file as well and look at this function, but you can see a bunch of things it's doing, which not everything is important right now for you to understand. I'll tell you exactly the line which is important. But what at a high level it's doing is that maybe if the instructions are the instructions which are decoded into multiple micro-ops, in that case it has something called micro PC, which RISC-V is, those RISC-V instructions are not decoded into micro-ops in gem5, so none of that part is getting executed here. But if your ISA had instructions which will be decoded into micro-ops, it might be taken care of here. Let's not worry about that right now. Similarly, if you don't have enough bytes, you might want to get more bytes from the instruction cache. All of that stuff is handled here. If you keep going down, I think the main thing that is important for us is line number, okay, I think I missed that line. Let's quickly go back to our trace. So from pre-execute, we call the decode function, right? Did we miss the decode function? Exactly here. So this is where we're calling decoder's decode function. And if you go inside that function, again, you can, in your VS Code, you can just right-click to go to that function and make sure you go to the RISC-V specific function. And if you go there, you can see inside that function, again, the main thing that is happening, it's just returning a decode call, which is now from the ISA subsystem. Now, I go back to my backtrace. So from pre-execute, there are a couple of decode calls. Again, not super important to understand what's happening there, right? The main point that I want to make here is the CPU did something in the pre-execute function, which eventually led to the ISA subsystem's decode function being called. And I think I'll now jump to this decode inst function in the decoder file. Sorry, in the ISA subsystem. And Okay, I think we have run into a small problem here. I don't have the build files for RISC-V here. Do we have a build?
Just build it real fast. Those files will show up the first thing, and then you put the files in your folder on the list. So everybody else might want to, in a separate terminal, hit the plus button they asked to show them how to build.
Yeah.
In a separate terminal, you might want to build.
So I think they all probably already have built it, right? Do you already, in your build directory, do you see a RISC-V folder? Cool. I don't because I did not build it when I told you. I just used the one that is already installed. So let me quickly build it here as well. Oops, I'm using wrong number of cores. Okay. So I've started to build it, and luckily the first thing, it directly populates all those files that are in the build folder. Can anyone answer me why the ISA specific files are in the build folder? Why they were not in the source folder? Exactly. That's why. So they are. So in gem5 we have this DSL, which is kind of from, and we have a source-to-source compiler, so it converts that into this C++ code, which then goes to the build directory whenever you try to build gem5, and then from that build directory, those source files, you get your eventual gem5 binary. Okay, so what I was trying to show you all, I'm gonna. So in your build directory, in RISC-V, you will see arc or arch RISC-V, and then you might see here wait, I think it's still not generated. I'm using the wrong. Okay, seems to. Sorry? It's still working. Yeah. No, I think it's usually there should be RISC-V and then generated folder here. Yeah. Wait. Okay. I was at some point. Get all the way back. Yeah, sure.
Why don't we just take 5 while we're waiting for this to compile? There's some.
Yeah.
Okay, everyone, let's come back. Sorry about that, everyone. Let's come back. One quick thing. If you have build RISC-V gem5.off, use that with GDB because it will give you all the specific line numbers and everything that is on your specific machine, which might be slightly different than what you see.
Yes. So as Jason said, make sure that you're using the binary that you just built on your machines or your environment. My binary is still building, but at least I am able to get the generated files that we needed, those ISO-specific files to kind of go through those functions, the ISO system functions we were talking about. So coming back to, or kind of summarizing what we discussed, we looked at, we put a breakpoint at the decode function and the execute function of add instruction in the ISO subsystem, right? And then the first breakpoint hit, and we looked at the backtrace to see what were the functions that got executed before that call, specifically from the CPU, what made that ISO system function being triggered, which resulted in decoding of the instruction. So, and we looked at pre-execute, and we said, okay, there are some ISO-specific decode functions that are called. And finally, the important function I wanted to talk about was this decode inst function. And so technically, we don't have the source of this function. Rather, this goes to the build directory once you build it. So again, the thing I was discussing earlier, that in gem5, you specify the ISO specifications in some DSL, and then eventually that gets converted into C++ code, which happens once you generate your files or build your gem5 binary. OK, so let's go to that function. And this is in build specific to RISC-V folder. You will see a folder of generated files. And inside that folder of generated files, you will see a file called decode method.cc.inc. And inside that file, you will find this function called decode inst. And if you look here, again, we'll see how exactly this function or this code got in here after some time. But right now, just to give you some overview, or at least partial understanding of this, you can see it's basically like C switch statements, right? So you are basically depending on some fields, you're making some decisions. And these fields really are coming from your instruction bits themselves. So you look at the quadrant, which is the first 2 bits, and all that. There's basically a lot of nested switch statements. Again, we'll look exactly how do you come to a certain instruction. But in this function, inside this function, you can see that if you keep going to, actually my backtrace, because it's not using the same binary, so it's hard for me to get the exact line from the backtrace, so I have to search for it. You might be able to see the exact line for the add thing from your backtrace as well. So technically, this is where this function returned me an add object, right? So you can look at this. There are a couple of case statements. Again, through those nested case statements, we exactly at line number 1012, we returned a new add instruction. So in this file, by going through some instruction fields, the only thing you need to understand at this point is that you eventually returned an add object, or an add RISC-V instruction object. So you were able to decode and say, oh, this is an add instruction, take this static add instruction. Does that make sense? Right? So we're still trying to understand at a very the overview or the big high-level overview that how this flow is working. So do you understand, at least at this point, how the decoding part is kind of goes through, starting from the CPU all the way to the ISA subsystem? Okay, let's move to maybe the execute part now. So I had put a breakpoint at the decode function and the other one at the execute function. So I think if I just continue at this point, I should then hit the execute, assuming, well, not just assuming, because I know that it's a timing simple CPU, it should really execute everything. Like it should decode some instruction and then just execute it, right? So if I do that, I hit the second breakpoint. And you can see that I hit the add instruction here. Again, I'll do a backtrace. We'll not go through every function. Just look quickly at what the flow looks like, and maybe look at the execute function. So again, here, you can see that there really this backtrace actually is not the best backtrace, considering I guess it's missing some of the file paths. But the main point or the main takeaway is that the final thing, this add execute is basically being called by your execute function inside the timing simple CPU. So if I go back to my okay, so due to some reason, the backtrace did not show me this function, but this is the function I wanted to tell you about. Again, if you go to the timing simple CPU, timing.cc is the main code file for timing simple CPU. You will see that once you do the pre-execute, right, which is where we decoded the instruction, then there are a couple of checks here for memory specific instructions. And if it's not a memory specific instruction, at line number 877, you call an execute function. And if you see here, I'm calling execute of the static instruction. So that's how the CPU is talking to the ISA subsystem through the static instruction objects, right? Calling an execute function, which is specific to that static instruction. And that function will determine that for this particular instruction, what is the actual execution function, right? Does that make sense? Okay, and let's have a quick look at what's this execute function, which is the, like the static instruction execute function. This time again, I have opened, I think you don't have to worry about where this file is or try to open it. This is again an auto-generated file. And inside this file, there are each specific instruction, specific execute function, and our instruction is add instruction. So we have an execute function specific to that. And inside this add function, you can see the actual logic that is corresponding to what's the functionality of the instruction. So as you might guess, that there is some destination register or a variable corresponding to destination register and a couple of variables corresponding to source registers. And then you actually use the execution context. That's what we use to access the CPU state, right? And then a function of execution context to basically get the value of the this particular source register, both of the source registers, and then the operation is just adding the two, and then again use the execution context to write back the result. So that's the functionality of this instruction, right? Does this make sense? The main point I'm really trying to make here is that I want you to understand what are the interfaces here. So you use execution context when the ISA subsystem is trying to talk to the CPU. And we use the static instruction when the CPU tries to do something ISA system specific, right? When we call current static inst specific execute function in timing.cc file, if you remember, at this line 877. OK. So questions on just the basic flow of basic flow of an add instruction when it's going to be how it gets decoded and how it gets executed when running on some CPU.
So we first look at the decode method. It returns like capital A, D, E, like it returns like an object.
Yeah.
Add object. Where is that add object defined? What type of, where's that defined?
So that basically is a static instruction, and we'll actually see how exactly even that code is generated. Then where you where's the constructor of this object and all that. Actually, we'll see that in in maybe half an hour. Any other questions? No? OK. So we are also a little bit behind on time. I think let's do something which is for a different instruction, which is a load word instruction. And we'll not look at the decode part of it. Maybe we'll try to look at the execute part of it. So if you remember from yesterday, if you're using a load instruction on a timing CPU or timing simple CPU, which is going to use what kind of memory access? Timing access, right? And if you remember, those accesses usually happen in two phases, right? You start the access, and the access gets completed. So for a load word instruction or any memory instruction, really, the implementation of that instruction or the execute part of that instruction, if it's running on a timing CPU, would basically be done through two functions. I actually talked about those functions initially when I was talking about static instruction. If anyone remembers, I don't know if you does remember, but those are called initiate access and complete access. So let's maybe look a little bit into those two calls. And then I guess we probably would be able to move forward then. Maybe before that, one question. What if I was running this on atomic CPU? In that case, if it's a load instruction, do I really need an initiate access and a complete access? No, right? Because everything is going to happen in just one call or one sequence of function calls. So actually, in ISA specification as well, usually if you're running things on atomic CPU, you'll have just one function call corresponding to that. For memory instructions, it's just called the that because you don't use any. OK. So let's maybe do the same thing for a load word instruction. I'm going to see if my other binary is already built. If it is, I'll probably use that in the debug. Oh, seems like it is. Yeah. So I think I'm going to switch to that binary. I mean, I'm assuming you already are using the binary that you built in GDB. So what exactly I did earlier was it's taking a long time to read the symbols. Okay, so I'm going to put a breakpoint. I mean, if you're doing it as well, just make sure to put a couple of. I think you can even do in the same thing you're executing, because I'm sure there will be some load instruction after that add instruction. But what I'm going to do is I'm ignoring the decode part of load instruction. I'm just going to do or put a breakpoint on the initiate access and complete access part of the load instruction. So again, this load word is in the ISA subsystem. This is for this specific instruction. I have a function called initiate access, and another one which is called complete access. And then I'm going to run using my instruction trace, or the Python script I used earlier. And it stopped at whenever it hit the first initiate access. Now you see, it's telling me the complete path to that function, because I'm using the binary from the same working directory where it can find the path to the files where breakpoints are. But again, let's maybe look at the last few functions that got executed before this one. So basically what really happens is that once the timing CPU gets the instructions, it figures out, oh, it has to do pre-execute and decode the instruction, and figures out it's a load instruction, right? It really calls this initiate access inside, or the static instruction specific initiate access. So if I go back to the timing CPU source code, so actually right there where we saw our execute function getting called, right before that, we check if this instruction is a memory operation, right? So the other execute we looked at, that only gets executed if it's not a memory operation. But if it's a memory operation, at line 856, where this check is being made, the first thing you're doing is you're calling the initiate access of your static instruction. Does that make sense? Right? So as soon as you figure out it's a load instruction or a memory operation, you call the initiate access of the static instruction. So that means it has to be, the actual implementation of that has to be inside the ISA specific files. And if I show you that source, this is that source. So can you guess what's happening here? So the CPU called this function, right? But obviously, the instruction specific function. Different loads or stores might have different kind of initiate access. Mm-hmm. Exactly. Yeah, so it's using execution context to access some CPU state or some registers, and then starting the access. So first thing it has to do, it has to calculate the address from where it's going to load something, right? Obviously, only then it can start the access. So for initiate access to happen, we need to know the address where we want to get something from. So all it's doing is that it has a variable for effective address, initializes a couple of other variables, but then the source in RISC-V, your load instruction is really some immediate value that gets added into source register. That's your effective address, and you load from there. You're getting this RS1 from the execution context from the register of the CPU state, adding the offset to it, and then just calling this function, which actually starts the memory read. Okay, then the other thing that happens, or the other breakpoint we had was at, I'm just going to continue my execution, is at complete access. So I started my access, and then obviously at some point it got completed. At that point, now let me look at, again, this is the ISA specific complete access that got called. What happened before it? If I backtrace it, I can see that right before it, my CPU somehow got called, or it executed a function called complete data access. So it must have been that once the CPU got the data back from the caches, it probably would have known, oh, I have got some data. So that means it's time to say this instruction is completed for which I'm doing this load or getting this data from the caches or the memory system. Let's ask the ISA subsystem to write this data into the whatever register that it needs to be written back to, right? So let's have a quick look at the complete data access inside the timing simple CPU. It's defined in timing.cc at line 1053. And if I go there, sorry. I mean, this is that function. This complete function is that complete data access function. And it might do a lot of latency specific calculations and other kind of stuff. Depending on the memory system it accessed, it might do things. You don't have to worry about that at all. I think the most important thing is inside that function, then it says at line number 1053, okay, now let's call the complete access of the instruction. So this is calling the current static instructions complete access, right? And let's go to the complete access, like we looked at the initiate access, to see what is happening there. So what do you think is happening here? Any guesses? Yeah.
Yes, it's taking that packet, it's like parsing out the return that data to that mem value, taking that mem to that destination register, instead of finalizing that again, just giving that back through execution context.
Yeah, that's true. So really, if we go back to when we call this complete access in our CPU, this is what we pass the packet to this function call, right? So the actual data which will be in this packet. So in our execution, which is the ISA specific function, we get that data. Really, from that data, we read that value into a variable, put that into our destination register, and then just write into the CPU state. Or in other words, by using the execution context, we write into that actual register. This call is what is where this is happening. Execution context, specific set register operand. The final value is what we write there, right? Does that make sense? I mean, at a high level, does it make sense that you just complete access at this point, write that data back to your register for a load instruction? For store, you might be doing something else, or dependent on a specific kind of load instruction, you might do something else. So this was just a simple load word instruction. I think it might be good time to basically move to try to understand now how this code that we looked at, this ISA specific code, especially this, actually even, yeah, this code. First, why do you think this is not very well formatted code? I think someone answered this before as well. It's auto-generated, right? So I think this probably could be fixed, but yeah. So I think now is the time really to try to understand how this code is generated, because when you want to add your new instructions, so really when you add a new instruction, you are specifying these things. You're specifying how your instruction is going to be going to be decoded from some bytes, just a blob of bytes, and how or what exactly, how do you specify the execution, what exactly is the function of that instruction, right? Those are the couple of things you specify. So the question is, how does this code that we just looked at, this auto-generated code, how is this really generated? And the reason that probably you want to understand is because then you can know once you write something in or add something to the gem5 ISA specification DSL, what exactly you need to do to, like implement some specific code in C++. So I would say just let's take a 2 to 3 minute, just a 2-minute break. I would suggest that you just stay on your seats, just try to think whatever we have discussed, and then in the next thing I'm going to talk about, we're going to basically now see, we're going to go through some more slides and try to understand this mapping of gem5's domain-specific language and this code that we just saw, this ISA-specific code, or C++ code, which is specific to the ISA implementation. Does that make sense? OK.
So I have a slightly different suggestion other than staying in your seats. I'm quite tired. That was not enough caffeine. Why doesn't everybody stand up and we do some stretches together? Does anybody teach yoga? Anybody? Everyone stand up. There we go. Let's see what can we do. Really tired? We're going to raise our arms up. That's all I have. Yeah, you can't even hold your elbows as close in as you can. So what do you think it takes about 20, 25 minutes to go through? 20, 25 minutes lecture-y stuff. Then we'll take a bit longer of a break, and then Ayaz is going to give an example of actually how to implement an instruction that's not.
Okay. So I guess for the next 20, 25 minutes, what we are going to talk about is again very complicated stuff, but I'll try to deconstruct it or somehow make it easier for you to understand. But please, if you don't understand everything, that's okay. It usually takes sometimes a couple of iterations to really understand everything. But I'll try to emphasize on the important things that are good takeaways. Okay. So that at least in future, if you have to add instructions, you know where to go and look at. Okay, and how to make sense out of all these ways. Okay. So again, I think I kind of explained some of these things, but to just summarize or reiterate again, basically, this is the high-level flow for instruction definitions in gem5. So we have, through gem5 specific ISA DSL, we describe the specification of instructions, which includes both how they get decoded and how they get executed. Then we have a gem5 ISA parser, which takes those specification files, and it knows how to understand those files. And apart from what you specified, it also deduces a lot of other information dependent on the specifications you have, some of the information that is implied by those specifications. And then it generates some C++ code, basically, which then the gem5 compiler uses along with the other gem5 source to create the gem5 binary, and then you can just run it for your ISA. And if you added a new instruction, this binary will have your new instruction. Does that make sense? Any questions? No? OK. So the same two instructions which we looked at, let's maybe try to dig into them a little bit deeper. One of them was add instruction. The other one was load word instruction. And specification is pretty simple in RISC-V. You just add two source registers in case of add, push the result in the destination register. In case of load word, you just use the, you loaded something from memory, and the address is calculated based on what's in RS1 plus what's in the immediate field of your instruction. So usually you know that if you look at any instruction reference manual, it tells you how instructions are encoded. And in order to decode the instruction, you have to look at that encoding, and there are certain fields in the instruction which you look at to say, oh, yeah, this is this particular instruction. For example, in case of add, the actual how is it encoded? The values of different fields in the instruction are as shown in the top of the slide. So func7 field, which is the last 7 bits of the instruction, have to be 0. Then there are 5-bit fields for 2 source registers. Whatever is in those fields, specify which number of register you want to access. And then func3 field, which is a 3-bit field, has to be 0. And then you will have your destination register. And then in the top 7 bits, the opcode is the opcode. In case of gem5, here you see a little bit different thing. So in gem5, we call the first 2 bits cod and the rest as opcode. The reason to call the first 2 cod or quadrant is because in RISC-V, those 2 bits are used to determine if it's the compressed ISA extension. Okay? And similarly for load word, it's shown on the bottom of the slide. So really in gem5, to decode an instruction, given you have just some bits, 32 bits, right? What you need to do is you need to really figure out these highlighted things. You need to figure out the func7 is 0, func3 is 0, opcode is C, and cod is 3, right? These 4 things is what you need to determine. Similarly for load word, is what you need to figure out is the bottom 3 things. In gem5, how do you specify the instruction, or in gem5's domain-specific language, this decoding usually happens through something called decode blocks, which is very similar to C switch statements, which we looked at, which was from the auto-generated code. And these decode blocks, really what they do is that there's a keyword decode, then there is an opcode, which could be actually any field here. coming from the instruction itself. These fields are defined separately somewhere. And then if this opcode has some value, like maybe if it has 0 value, then you execute this part. If it has 1 value, then you execute the part corresponding to that. What is this format thing? I'll talk about that in a couple of slides. Don't worry about it. So really, to decode an add instruction, how you would really decode it is through a set of nested decode blocks, right? You need to figure out all those 4 fields, right, which we talked about. So what are those 4 fields? Quadrant, opcode, func3, func7. So in this slide, what I'm showing you is, especially those pointers or dots, they show a lot of code that is missing. So in actual specification file, you will, in the same decode function, you might be decoding many instructions, right? There might be many instructions which have the same quadrant or which have the same opcode. So all will be specified there. But in this case, we're only focusing on add instruction, right? So you have to look at those 4 fields. What exactly these fields mean would be usually defined in a separate file. We call that a declaration file. For example, in case of add, it's simple bit field. Quadrant means that the 0 to 1 bit of the instruction, of the 32-bit of instruction. Opcode means bit 2 to 6, right? Similarly, func3, func7 also specifies which bits. So these things, these fields you are looking at, they are specified somewhere. And really, to figure out if it's an add instruction, you first look at the quadrant. If it is 3, you then look at the opcode. And if it is C, you look at the func3 field. And if it is 0, you look at the func7 field. And when it's 0, you say, oh, I got my add instruction, right? And what's happening in this, once you figure out that this is an add instruction, right? At this point, you have correctly decoded, but you have to now create an object for it and say, oh, yeah, this is the add instruction. Usually, that happens through this call here. So this add, whatever you're seeing here, eventually would invoke a function call. And whatever is inside that parenthesis you're seeing is really a code literal. It's just a string. And that string is specifying what's the actual functionality of this instruction, OK? And we'll look at what it's translated into some real code and what does this really mean. So you understand till the point where I say that once you have figured out what instruction this is, you have to now invoke a function call. But what function call will be invoked to really interpret this string in some particular way or interpret these arguments in some way depend on the format that you are using here, OK? I'll talk about format in a little bit more. So again, to kind of summarize everything, right side is what is actually generated C++ code. This is the code which we looked at earlier as well when we were talking about how the add-ins would come to know of an add instruction, right? And the left side is the DSL specification or DSL code, which is how you figure out an add instruction, right? So you can see how there's a one-to-one mapping between all those decode blocks we were seeing at which we were looking at and the actual switch statements in C++. Now, and if you remember, there we saw that there was a return new add instruction, right? So we're returning an object. So really, to understand how from the left side, which is we just specified the functionality, to this thing, where we're returning an add instruction or an object to an add instruction, how does the ISA parser figures that out, or how exactly that code is generated? Because the rest seems pretty, like, you can follow it, but here it's not clear. So that's where the format magic comes in and all that stuff. So again, just to remind you, I said that on the left side, when you specify this, you are really invoking a function call. And the function call depends on what? The format you're using. In this case, what format are we using? It's called ROP. So that takes or brings us to the format blocks. So how do format blocks look like? So format blocks are really to basically kind of define how a class of instructions need to be, like decoded and interpreted. Not like in terms of actual interpreting a language or something. I'm talking more about like understanding what exactly this thing means. So format blocks really look like Python function calls, and they expect some arguments. And dependent on those arguments, then they generate some output. And this output is really what then goes into the generated C++ files. And the 4 kind of outputs they generate are the header output, the decoder output, the execute output, and the decode block output. We'll look at some examples of these, that what exactly, how exactly those outputs are generated, and what do they really mean. So technically, in order to generate, so this is now a real example of a format block from RISC-V's specification, our op format. So this is for all our R-type instructions. So as you might see here, I told you that, okay, there are 4 things you need to generate, which ultimately simply are 4 variables, and you can just pass some strings to them. And whatever those strings are, would get returned to the C++ code in the corresponding places, which each of these are responsible for, right? But normally, it's not, you don't just pass a string to them. You rather use templates. And the main idea is basically to reduce the amount of code and try to find overlap between different types of instructions and kind of define them in the same way, right? So for all R-type instructions in RISC-V, you will use this format. Again, so what are we really assigning to these 4 variables? We are assigning 4 strings, but those strings will be coming from some template, and we'll really be specializing those templates by substituting some object into those templates. We'll look at some examples that will make more sense. Okay. Again, as I said, these are template blocks, simply doing string assignments. And what are we passing to these template blocks? We're passing IOP, which is an object, which we created at the top of this function, or top of this format block, right? This is an object of the inst obj params class. You might wonder why that is needed. So usually, you could have just pass again in this argument here, any string. It would automatically be substituted in the corresponding place in your template. But usually, this is done through, in case of gem5, the ISA parser actually relies on this inst obj params class, which is really there to encapsulate the certain characteristics of an instruction. You will specify some information. The ISA parser will itself generate or come up with some other information about the instruction, and we'll use that information to basically then substitute in those templates to give the final code. We'll look at some examples, so don't be too much worried if not much of this made sense. So an example of a template. This is the basic decode template. So this template is going to create the code which will go into in our C++ code. From the name, what do you think? Like, to what part of the C++ code it's probably going to go to? It's basic decode template, so just from the name, it's a decode block. Yeah, so the part of the code which is really responsible for decoding the instruction, this is where this will go to, the code that is generated by it. So so really, in this template, what we're doing is we are returning. So as I told you earlier, that it's really this template is going to be, we are specializing the template, and it's really used to return a string, nothing else. It's nothing complicated or I should say magic or anything. It's just some string, which is hopefully the C++ code that we want in our C++ files. So you simply, in this case, are returning new And in the template, you have a symbol called class name, which you want to be specialized or you want something else to go there. So let's look at the mapping of this decode template to the actually generated code. This inst obj params, no need to worry about it. So in the case of our we class name, if you go back to your template, the class name we are using is add. This is the same class name that corresponds to the mnemonic of instruction. So actually, let me quickly go to the actually generated thing. So this left side again, our entire decode logic for the specification in the DSL. Right side is the actually generated C++ code, right? So you can see that the once we called or we invoked the function on add through that format, our op, it really, in order to create the basic or create the decode part of our C++ code, it used the template basic decode, which was really doing return new, then some symbol, class name, and then machine inst, right? And that symbol in this particular case, because it's an add instruction, we replace that with add. So that's why the generated code is really showing you return new add, right? So if it was some other ROP instruction, that name would go there. So the decode in that case would simply return an object to that class, right? Does that make sense? I mean, this is, so this kind of thing happens in a lot of places in the ISA description. So this is for decode template. We similarly have execute templates, constructor templates, and other templates. I'm trying to focus a little bit more here because then I'm going to quickly go through some examples of other templates. But again, you don't have to understand too much of how they're really specified. As long as you understand the mapping between the two, I think you'll be able to figure out exactly how they're used. OK. So let's try to go through some other templates. And why those templates? Really because if you remember the format block, I told you that it generates 4 different kind of code pieces or code blocks. We just looked at the decode block. It also generates execute output, right? Which is probably one of the other most important C++ code that is going to be there corresponding to an instruction. So for this, again, we have to specialize now the basic execute template. And this is the basic execute template. So in the gem5's ISA DSL, the basic execute template really has 4 symbols that need to be specialized. Or in other words, there are 4 pieces for which you need to have like some actual C++ code. Or the code of the execute function will be defined or will be implemented through 4 different pieces. OK. What are those 4 pieces? So the first symbol here is the op decl, which is for operand declaration. Then you have another symbol which is for the operand reading. Then you have a symbol for actually executing the code, which corresponds to the execution of the instruction. And then an operand symbol for, or then a symbol for write back. And really, it's only the code symbol that you specify once you are specifying, or once we specify the add instruction. All the other 3 symbols are auto-generated, or in other words, come from the ISA parser. Generally, you will not be specifying them. ISA parser, dependent on the format of the instruction, will automatically figure out what should those be, right? For example, if you specify that the logic of the instruction or the execute part is take a sum of these 2 source registers, put the result in the destination register. ISA parser will figure out, OK, these 2 source registers should be are my 2 operands, so I need to declare them in my execute function, right? So it will automatically figure out what code should be there. Actually generated code, so this is from the C++ code. Corresponding to that template, this is what we got once the ISA parser built it for us. So for execute instruction, the topmost part is, again, declare the operands. I mean, we looked at this code, right? So the topmost part was declare the operands, then the next symbol is for reading the operands, then the code for the instruction, the actual execute code, and then just writing back the operands. Any questions? Are you able to, are you able to follow to some extent? I think as long as you're able to get some idea, believe me, it does take some time to get through all of this. It's arguably one of the pretty complicated parts of gem5. So if you get some idea, you can always go back to the slides, try to get better understanding. And if you have to use this part of the system, you at least know what to do. Similarly, there's declare template. Let's not worry about it. Again, from some template, you are basically, by specializing it, generating some C++ code. That's the entire idea. For constructor template, we're not going to go again there. The only thing I want to talk about is the difference. What's the difference for memory operations, right? We saw for memory operations, the execute part is still a little bit different, right? It really depends on the CPU model you're using. You might just execute it in one go, or you might execute it as two separate functions. So that's where we have three new kind of templates. We have just simple execute, like execute everything, or we have initiate access template and complete access template. And as you might have already guessed, that full execution template is when you are using the atomic mode of memory accesses, and the other two templates, you use them when you're using the timing memory accesses, right? So we're going to look at from the load execute template to the generated load execute code. If it's hard to follow here, the code, you can always look at the slides. So look at how from some template the code is generated. Again, the first part, which is the declare the operands, is simple to follow. Then reading the operand, in this case, you just read the thing from the execution context, right? That registers value. You compute the effective address. Here is one interesting thing that I want to talk about. So EA underscore code is also symbol, right? The other symbols, which said ISA parser is automatically going to figure out what code or what is the equivalent code to that symbol. The EA code symbol we specify, at least in case of our in load format. So in your specification, as shown on the top of the slide, when we define the load format, we also said EA code symbol is equal to this string, which is basically simply a variable EA equals to RS1 plus a variable offset, right? So in our operand declaration part, we already would probably have these things declared. Now we're just using them to compute the effective address. So your load execute templates EA code part gets converted into, as shown on the right side, that simple statement. And then you simply, there's a function called to do read memory atomic LE. Here stands for little endian. This entire code is basically from your template is going as it is. Like there's no change at all. And then you have a symbol corresponding to the actual memory access code, and then something for write back. So one thing you might have noticed here, all of this happened, everything happened in one function. We computed the effective address, got the data from memory, write it back to the register, right? So if an atomic CPU want to use a load instruction, want to execute a load instruction, it should use this execute function, right? Does that make sense? But if we are not using atomic CPU, then the other kind of CPUs will be using two different kind of functions, which we define through two other templates. One is load initiate access template, and the other is load complete access template. So in load initiate access, the only thing you're doing, declaring the operands, getting the value of source one register, just computing the effective address, and just starting the memory read operation. Telling the CPU, just start the memory reading, nothing else. We don't know anything else at this point. At some point, we'll get a response back, then we'll think what to do. So that's,
Sorry, is timing implication
So this is just the execute part or the ISA specific part. So the timing information, that responsibility of your memory model or the CPU model to how to track the timing information based. So this is just corresponding to the actual execution part of the instruction. Yeah. So similarly, for load, the completion of the access then is being done through the complete access template. We don't need to go through it. You already, I guess, kind of know. You will be first declaring your operands or declaring some variables, getting the data from some packet, which the CPU who's using this instruction will load into. You will put that data into some variable, will write that to your register, and things done. So really, do you get the idea that in ISA specification, sometimes we do specify ourselves, okay, this is equivalent to this thing, and sometimes the ISA parser figures it out by itself, that what this symbol should be equal to, and as a result, we get the C++ code that is shown on the right side of these slides. So that's the key idea here. I think a couple of other quick things that I want to talk about. We already talked about bit field definitions, that in the ISA description system, you can, all the bit fields we saw earlier, they're also defined in declaration files. A couple of quick things that I want to talk about. One of them is the operands. So all the operands we are using, so how does ISA parser really figures out what, given that this instruction is using some operand, what kind of declaration code to generate? It really figures that out by the properties of the operands. Like if it's a memory operand, or if it's a simple register operand, or like maybe you can also define some part of a register, not the entire register. So you can define any kind of operand you want. And this definition of operands is usually through Python dictionary, which basically each operand there, as you can see, the key is just the operand, and the value is actually tuple of 5 elements. The first one there is the class of the operand. The second one there is the default type of the operand. This type here is really equivalent to your C++ data type. And actually, next couple of slides, I think we have what exactly UD stands for. But then the next element is the bit field name. It specifies out of 32-bit instruction to access this particular operand, what part of the field or the instruction are you going to be using. Then the next is the type of the operand. Like if it's an integer register, this type is just a string is integer. It could be memory operand, could be float operand. And then the last thing is if you disassemble this instruction, in what order do you want this operand to be printed? And finally, the operand types. There are multiple operand types. If you want to access only part of the register, you can specify the register through these operand types. Like ASB is simply the 8-bit integer, UB is unsigned 8-bit integer, and so on. So just to give you an idea that there's multiple ways to specify or qualify an operand to some specific type. OK, so I think this covers the ISA specification part. Next part, which I think we're going to do after a small break, is where we will try to add an instruction. So I've tried, well, randomly we picked the packed SIMD instructions for RISC-V. Luckily, they are not hard instructions to add. We'll be touching a very small part of this ISA specification we talked about, where we're really going to be adding the instruction. But I think it was important for you to understand what all those other things mean, because even that small part will be using things from those other things or the other components. So if you have any questions on the gem5's ISA DSL, or how do different components interact, or how does that get translated into C++ code, let me know. Other than that, I think in how long break?
Be back at 3:20.
OK, yeah, at 3:20, I think we'll start adding some code. So luckily, I mean, it's not a complicated instruction, so it's not going to be too big of an issue. I'll also tell you about some other instructions you can add. And maybe we'll just keep them as assignment, and I'll give you the test binaries, and you can test on your own, and let us know if they worked, or if they did not. We can figure out why they did not. Okay?
So I want to get going on this. So we can get throughout, hopefully not too much after 4. But I know I am really excited about this part. This is adding an instruction is something I've never done in gem5. So it's cool to see somebody else explain how to do it, so I can learn how it works. It's also kind of cool, since RISC-V has so many extensions, kind of pick one that's unimplemented in gem5 yet and implement it. And I don't have time for you all to implement one and us to help you too much along the way, but I think Hgih has enough structure that he can kind of give it to you, and if you get bored tonight, you can work on that and we can talk about it tomorrow. All right, cool. I'll turn it back over to you, Alice.
All right, thank you. Okay, so let's start adding an instruction. And what we're going to add today is basically an instruction from RISC-V backed SIMD extension. So this extension basically is focused on low power systems or DSPs, and mainly used for subvert level parallelism. So the idea is that you use a general purpose registers, but then you can operate on different data elements inside that register in parallel. Okay? So you can do multiple operations, and usually small systems where your data types are usually never, let's say, more than 16 bits, you can do many operations by using one 64-bit register. So just to give you a picture of the instruction, how do they work? Let's say you have a 64-bit register. Now you can, or two 64-bit registers, you can basically operate on 16-bit elements, which will be 4 of them in a 64-bit register in parallel, and the results will go to another 64-bit register. Any questions on the basics of this instruction extension? How does it work? Make sense? Okay. So the instruction we are going to look at right now is, I think, probably the simple. Yeah. I think there are few instructions where it can be different, but for majority of the instructions in this ISA extension, they have to be the same. Yeah, but there are few where you can actually, I think, do add and then probably, multiply and then add, that kind of stuff. But we are not touching those instructions at all. So we're probably starting with one of the simplest instructions, where it has to be the same operation. But then there could be different variants of an instruction where you could specify what do you want to do if there's an overflow and that kind of stuff. The particular instruction we're going to be implementing right now is the simplest, where if there's an overflow, you just ignore it. So from the instruction reference manual, this is the description. It tells you how this instruction is encoded. These are different bit fields. So the first 7, or from the left side, the 7 bits are the funct7 field, right? Similar to the add instruction we saw earlier in gem5. Then there's funct3 field. Then you have an opcode field in the upper 7 bits, and then a quadrant field, right? So we're going to use these things and try to, first of all, decode and figure out when do we really get this instruction. So let's go to the code. So I'm going to the ISA description file, and if you go to the source architecture RISC-V, then inside the ISA folder, you will find a lot of .isa format files. These are all the ISA specification files, or this is the gem5's DSL through which you specify an instruction. So, okay. So if you look at this file, it really starts with you first of all decode or look at the quadrant field, which was the first 2 bits. Does anyone remember what it was? Oh, you can see now. So it's last 2 bits, yeah. And those have to be 1, 1 in binary. So first of all, actually there are a lot of, I guess there are going to be other instructions which have the same quadrant field. So we need to find out that block, and inside that block we'll add our own thing. So you start looking at quadrant. So first, like the first thing is quadrant. If it is 0, then you go to this block. So we need to find out where is the 0x11 block. So you keep going down. So I'm going to, keep scrolling down. Did I make a change here? Let me make sure there's no change. Okay. Yes. So that was 0, 0. Now we have just found the 0x1 block where the quadrant is 1. That's not what we are looking for. We need to keep going down. Then this is the quadrant 2 block.
Is it 256 collapsed?
Sir?
Collapsed that line 256? Also line 256? Like that 256 collapsed. The line 256.
Uh-huh.
There's like a little arrow.
Yeah, that arrow.
Yeah, I can like collapse it and I'll take you right to the next. So if you go to
You said there's an error on line 256? Oh, sorry. Okay. Yeah. Sorry about that. Yeah. So we got to the block we are looking for, right? Does that make sense? So we wanted the first 2 bits to be 1, 1, the quadrant bits, 0x3. Okay? So at this point, once you have figured out the quadrant is 0x3, the next thing you look at is the opcode. Anyone remembers what was the opcode? Let's go back. So it is 1101. What does that stand for? Sorry? Should be 1D, right? Right? Am I correct? Okay. So, gosh. Yeah, so let's zero x3. Sorry, yeah, we are here in the opcode thing. And actually, I mean, we don't even need to go anywhere. We can just decode it here, right? So we know our opcode. Well, I want to make sure that there's no other instruction with the same opcode, so let me quickly verify that. Actually, I'm pretty sure there is nothing else. So we can just add it here. So the opcode we are looking for is what? 0x1D. So just to be consistent, I'll go with the, I think for hex, they're just using lowercase letter. And so I've got this. Now, if we're done with the quad field, we're done with the opcode field. The other 2 fields are func3 and func7 fields, right? So let's first look at the func3 field, which I'm pretty sure was 0. Does anyone think I'm wrong? Does anyone think that's not correct? Okay. So let's do this. 0. Okay. At this point, I think we are where we can decode this funct7 field, which is this 7-bit field. And I think in hex, it translates to 0x20. Okay. Any questions? Mm-hmm. Yes. Okay. So we have looked at the quad field. We have looked at the opcode field, which was 1D. We have looked at the funct3 field, which was 0. We have looked at the funct7 field, which was 20 in hex. So at this point, we know we have got our instruction. So you can now call your instruction whatever you want to call it, right? The mnemonic you want to use, you can use whatever you want. Well, technically, it shouldn't be whatever. It should be whatever will be in the binary, right? Whatever the compiler would use. In our case, we are a little bit flexible. I'll tell you why later, because the binary we have is flexible. But I'm calling it add 16. This is my SIMD add instruction. So I'm calling it 16, add 16, because it operates on 16 bits in parallel. And really what you do here is this, it's like a function call, as we said earlier. But then inside the function call is where we'll start having our real instruction specification. But that has to be inside these double braces, and it, so that the ISA parser will figure out, OK, this is really a string, and I need to, from this string, figure out what's the actually the code that's going to be executed. But before we actually put any code here, or a string which will correspond or specify the actual implementation of the function, there is one thing that I kind of did not do it here yet. So if you remember, we said all the instructions, they have to specify or follow some format so that the ISA parser would know how really to interpret the string or the specification you are going to be writing here, how to really figure out from that specification what this is really meant to be. And really this, in this case, because we're just accessing registers, so it's really our op format is what we're going to be using. Also because it's like instruction is being executed just as a single macro instruction. So usually that format block, you can specify it anywhere. If you specify it around multiple decode blocks, that will mean everything inside those decode blocks will follow that format. Let's just do that here maybe. Like, that's done in a lot of other blocks in this file, but I'm just doing it here. And really, it is also a separate block. So, OK. Makes sense? So just added this format block around this thing. I think I missed oh, yeah, this parenthesis has to be here. After the parenthesis? Yeah, there has to be one. And inside the parentheses, what you really specify or pass is this. Also, I think it could just go up there. This double braces where we'll have our code, and usually you can also specify the class of this operation. I think by default it considers everything as int ALUOP or something. But if you want it to be something else, you can, apart from that string we are passing, you can also pass that. We are going to be passing int ALUOP. Just making sure that it's really called int ALUOP. Yes. So this is just saying that this class is this instruction belongs to the class of integer ALU operations. Okay. So going back to now actual implementation of the instruction. So what I'm going to be doing here, as you might remember that all our operands or the registers we can use, they are all specified in the declaration files. You can always look at a particular name of the operand, how many bits of a register does it correspond to, and that kind of stuff. But by default, I mean, you can also just trust what I'm saying, that if you use underscore SD qualifier, sorry, underscore UD qualifier, which is I think by the default qualifier, that usually means 64 bits of the register. And you could access, you can use a different qualifier to access smaller number of bits. But in this case, what we really want to do, we have a 64-bit register, right? 2 of them. And we want to access 16 bits, 16 bits, 16 bits, and 16 bits for both the registers, and then just take sum of those. And whatever the result is, we're just going to put them back in our 64-bit register, right? And because this particular variant of this add 16 instruction, it just ignores the overflows, so it's super simple to implement. We don't have to, if something overflows, we don't have to worry about it. So the way I'm going to do it is, let's start with, again, this is one implementation. You could think of much better ways to do it. But let's just create a variable. I'm going to call it rd16. And what I'm going to start doing is I'm going to read the first 16 bits of my first operand. And to access that, you can say rs1 underscore UD. So this is rs1 is source register, underscore UD is just saying I want to access all the 64 bits of the source register. So there's one issue that you might think of, like maybe using 16-bit here and then later 64 bits. So I think the ISA parser doesn't like it. It really wants you to basically, if you specify this, the actual register name, it has to be the same number of bits. Or in other words, like if you say I'm using rs1 underscore UD, then that's the only thing it's going to read from the execution context or through the execution context. Mm-hmm.
My first time seeing this. So because of that, because it's only going to read the register once.
Yeah.
And you want to read all 64 bits. That's why you use rs1 underscore UD.
Yeah.
Instead of rs1 underscore HD or
Yeah.
whatever to get a half word.
Yeah, exactly. So I'm going to get all the 64 bits once, and then I'll just play with them and extract my 16 bits. So the first, obviously, we need to do 4 parallel adds, right? So I'm doing the first add right now, just getting the first 16 bits. So I got them from the rs1 UD, and I also get them from rs2 UD. Oh, sorry. Let's not worry about the line length right now. Okay, so hopefully this is going to do the first operation. The next is getting, I'm going to create another variable. Let's call it rd32. What I'm really doing here is, again, making sure my data type, or I just stay to 16 bits. Again, taking the rs1 UD which was the all 64 bits, just shifting it to the right by 16 bits. So the ones we have already used are out of that 64-bit number. And because I have casted it to 16 bits, so that out of all the remaining 64 minus 16 bits, whatever is left, I only get the lowest most 16 bits. Make sense? We'll do it for the second one as well. Are you able to follow what's happening? OK. Cool. Anyone has a question? If anyone is not able to understand, and then if someone is able to understand, can someone who is able to understand just explain it louder? OK, so I think almost I got for variables. Again, this is just one way to write code. I mean, you could do it much more smartly, I guess. OK, I think I have most of it implemented. Let me just go through it once again. So I'm reading first of all, the first 16 bits from both variables, putting them in variable by taking sum. Then I get the next 16 bits, both the variables, put them in another variable, then get the next 16 bits, then get the next 16 bits. Put all those 4 results in 4 variables. Then from those 4 variables, I'm going to construct my result. And I start with like putting the leftmost 16 bits first, and then I keep on shifting it by 16 and just taking an OR with whatever is the next 16 bits that should be added. And then finally, I put this result in the actual register, which is the RD register. The reason I mean, you could have said, why not just like say RD equals to RD underscore 64 and just keep on updating it. The problem is that we merely want the way ISA parser and the subsystem will interpret that is like you are accessing that register multiple times, and it might try to access that from the execution context. Actually, if you print the debug trace, by doing that, you will see your destination register printed 2 times. So that's not really the correct implementation you might want. So that's why usually we will have like in some temporary variable, we're just putting the result and then just The actual destination register, which the ISA knows is a destination register, will write the result there only once. Okay, so got the, I think, the functionality of the instruction. Questions? Mm-hmm.
Is it possible, like, for sort of repetitive, like this is sort of a repetitive instruction. Would it be possible to use like loops and stuff inside here?
Yeah. So so for the execution specification, you can use, I think, loops. But if you want that behavior, like a hardware behavior, then probably you are looking for micro-ops. So that way you want to implement your instruction differently through micro-ops. In this way, we are implemented the instruction as a single instruction, but the specification of the instruction is taking multiple lines of code, which could be any complex code as well. Yeah. Yeah.
So in Snapper, you could also implement your custom instruction.
Sorry, say that again?
So if we want, like, to implement a custom instruction using micro-ops,
Mm-hmm.
and different, use our own micro-ops.
Yeah, exactly. You can specify your own micro-ops. Exactly. Okay. I think this should work. Let's try to compile it. If there is some error, hopefully we'll figure that out, fix it, and try to test it. I'm going to try to compile it, and meanwhile, if you have any questions, you can let me know. So we have so these packed SIMD instructions are yet not part of the mainline GCC. So like if you just try to get these instructions in a binary, it's not possible. There are some custom tool chains that some companies have that you can use to basically get these or use these instructions. Or the other possibility is like to maybe change the tool chain yourself, which I did, change the assembler, and using some inline assembly tests using these instructions, I got those compiled into a binary. So here I'm directly providing those binaries to you. So we have a test for add 16 instruction. There is another test for a shift instruction, which I was planning that you will do, but I think we might not have enough time, but I think you can do that as an assignment. I have that test already in this directory, in the materials directory, which correspond to this particular session. Right now, once this compiles, we'll try to use that test and run it with our trace script to see if it works. So the tests, the way, actually let me quickly show you the what's happening in the tests. I have the source as well, but I'm giving you the compiled binary as well. Uh-huh.
So what you do when you skip some steps, right, and you just put everything all in one, is that right? Because like in the RISC-V you have like execute and then
We have execute function and all that.
right.
Yeah, so I was basically showing you earlier that how the thing we have specified here, actually once it compiles, we can look at the thing we specify. So usually to specify an instruction, you normally just have to specify in the ISA DSL. Sometimes the DSL might not be enough for you to, depending on the instruction you're trying to specify, you might have to extend it or add new formats. A lot of times you can just make use of the existing formats. But also to figure out how exactly your instruction will interact with CPU, you need to understand this entire flow.
So then, if say that was a load 16, like
Got it?
SIMD, would you also need to like create the initiate access and compute access, or would that be generated?
Yeah, for all.
Generated for you?
So, from the specification you will have and the format that you're using, that will determine what will happen. So in that case, you might have to add a new format if you are trying to do that as a single instruction. So if you're trying to do it as through 4 independent load operations, you might be able to use the format load, because that right now it expects that it's just going to do 1 load, right?
So how do you know when you have to do that? It's just like compile and then it just gives you a 0? Like, how do you know if you have to expand on like the?
Oh, if you have to use a new format?
Yeah.
So that's why I think it's important to kind of know what format you're using. That's why I was trying to explain to you guys like what, from a format, how do you get generated code, right? So every format basically really is generating some blocks of code. It has some templates. So if you look at that format, the templates it's using will determine what exactly is going to be generated. You can also look at the generated code to see if it has the code that you wish it has, right? So all those things like kind of connect together. So the tests I have, they are in materials, developing gem5 models, CPU instructions, and then there's a directory called tests, and it has the code as well as the binary that I've already made for you. You can look at the code, but really these are inline assembly, single inline assembly instruction. So really you can look at the numbers. I use 2 numbers, all ones, and if you want to add them, obviously we're ignoring the overflow in this particular version of add 16 instruction. The output should be FFE in each 16-bit location. So this should be the output. Let's actually try to run this and see if we do get it. So let's try to make sure I'm using the absolute path. And then my tests. It's in materials, developing gem5 models. Is that correct? Yeah. CPU instructions. 6 CPU instructions, tests, and then the test is called add 16 underscore test. Okay. Let's hope that it does what it should do. Okay, this is not the correct path. Let's confirm this works. Bootcamp environment. Oh, it's materials. Okay, so with this binary, I just ran the test. Do you see it says test passed? So it worked. Yeah, so you can see it printed that we are trying to add 2 numbers, right? These 264 bits are all ones. So if you add them, you basically adding corresponding 16-bit, 16-bit, right? And this particular version is just ignoring the overflows. So as a result, what do you get is FFE, right? So that's our output, and it's good. So first, any questions till this point?
Did you have everything in one file because it was atomic thing? Before, say, timing, did you have add different functions to say read this register and then?
If you use timing,
Right. Would you have done the same thing?
yeah, so because in this instruction, it's just accessing registers, right? There's, it's not accessing memory. So same should work with timing CPUs. But if it's memory, then you will have to have your execute in that case has to have atomic specific function and a timing specific, two timing specific, which is initiate access and complete access. But you will not write those functions. You will just specify a format in the ISA DSL. And that format that you will specify will create those functions for you. But if you want to do something where, let's say, those functions need to be called in a different way, maybe multiple times, then you might have to add a new format to do that, right? So that's where I think it becomes important to understand how formats are really used. So any other questions? So we're getting very close to 4. I mean, I'll stay here as long as you want to talk about this, any questions you have, anything else. But I'll try to conclude the things that I have here so that the ones who want to leave, they can. So I have an assignment for you, which is going back to the slides. So we did this add 16 instruction. We tested it. I showed you the test binary. The assignment for you, which we were planning to do here, unfortunately, things didn't go that well. So there's this shift instruction. I'm not going to tell you what this does. What does this do? I'm just giving you the instruction reference manual. So it's your job to look for this instruction in the manual, figure out what specific variants this instruction has, what do they do. You don't have to implement all the variants, maybe implement one. Actually, the test I have is only for one variant, the simplest variant. So your job is to figure out how the instruction is encoded, what does it do, and then implement that in gem5. It's very similar to what we did for add instruction. So your job is to implement that, and then in the tests directory in this folder corresponding to this module, we have a test for SRA16 test binary, which is a test you can use to test your instruction. So once you run that, it should say test passed. If it doesn't, that means there's something wrong in your implementation. If that's the case, let me know. We'll try to fix it and see what error you might be making in your code. Okay? So once you are able to do that, let's actually try to add more RISC-V packed SIMD instructions. A lot of them are very simple to implement. I just want all of you to contribute as well. If you implement any instruction and tell me to give you a test binary, I'll give you the test binary. I'll generate it for you. You don't have to worry about assembler part or anything. I'll add it for you. I'll give you the test binary that you can use to test the code you have. Okay? You just have to implement the instruction. And one part that I'm, again, not going to be talking about right now, you can look in the slides, is how did I generate the binaries. It's something which I would suggest you look at, because it took me like a couple of weeks at least to figure out really exactly how to do that, because we still don't have support for these instructions in mainline GCC or any mainline compiler. So I had to modify the assembler. There is some source available online how to do that. It took me some time to figure that out. But I have tried to write down a short tutorial in the slides for you to basically see how exactly you would make or change the assembler if you want to test or create a binary for your new instruction. But I'm giving this offer that if you want to implement instruction, I can do it for you. But yeah, just add some new instructions. We can create a shared file or something where if someone is going to add something, just put or write down that I'm going to add this instruction. So if someone else is going to add some instruction, just make sure someone else is already not working on it. Yeah, so we'll do that on Slack. Just want to point out it here, but we'll hopefully create a list on Slack. I don't know how many of you are really motivated to do that, but I think it could be a fun exercise. While doing that, you might, if you get a chance to go back through the slides and then you figure out you have more questions, just let me know. I'll try to explain remotely or in person. OK, yeah, so that's it. But if you have any questions on the instruction we implemented, or if you want to implement the new instruction, the room is going to be on right now, but if you want to sit outside and implement it, I can help you. OK? Any questions? OK? Yeah, I'm here, standing here. If you think of questions later.
Great, thank you guys. All right, I have a few questions for y'all, and maybe a couple of announcements. So I want to make sure a couple of resources that I want to make sure you're aware of. Let's see. So first, on the gem5 website, there's lots of documentation. Not all of it is 100% up to date, but there's a lot of documentation. One thing I want to point out is if you click documentation and learning gem5, and then click on modifying and extending, this is a prose-based thing of what Mayar went over this morning. So if you learn better by reading prose, you can read through this and get the same thing that Mayar did this morning. As well as going a little bit deeper or further and making a full cache. Same thing here tomorrow. When I go over the Ruby stuff, I'm not going to go through all these details because it would take all day. So we're going to skip over some things. But if you want to read about all of it, I wrote a lot of words writing this stuff a few years ago. So that's it. One other piece of documentation that might be useful is doxygen.gem5.org. So this is doxy-gem. So it's like oxygen plus documentation together, doxygen. So here, for instance, I think Mayar was talking about SimObject. If you search for SimObject here, go to the SimObject. This shows you all the SimObjects in Gem5, which is a lot. Scroll down somewhere. And so here in this detailed description, this goes over what Mayar was talking about with like the order that things happen. Where like init is called, then reg stats, then init state or load state, then reset stats, then startup, then drain resume. So it kind of talks about how SimObjects work. And there's a lot of other code-based documentation you can find in the Doxygen as well. Any questions on those documentation resources? Okay. One other announce, or a couple other quick announcements. Don't let me forget. I really want to get a picture of everybody like outside tomorrow morning. So do your hair. Wear a nice shirt. Tomorrow morning we'll get a picture. Let's see. So how many people would be interested in having a one-on-one 15-minute office hour with me? To talk about the research that you want to do with Gem5, and I can give you some specific advice potentially. How many people would want that? So, sorry, let me rephrase this. If I were to do this, how many slots will I need available? Okay, let's flip the parity. Who would not want to do that? Who is like totally fine with not like this? Who would not participate in that? Okay, so it sounds like I need a lot of slots available. I think I can generate 32 slots, which will cover we'll probably